easy for you guys, and you can follow me with the example and all this lecture. And at the end, hopefully, it should be very easy for everybody. Okay, as you might remember, in order to consider or design a column, we have two actually categories for the column. One, short columns. It means that buckling is not that important. Is not important. So the column can reaches to maximum load. So if in future somebody asks you for one of these IT exams or P exams, we have the same size columns, and the rebar, everything is the same. And one of them is slender, another is not. So which one can carry more load? So with no doubt, the one that is short column. So it's obvious, and I think hopefully it's not that big problem. But the problem is, okay, how can we calculate the loading for a slender column? That's the question. How can we calculate the load on a slender column? How much it can tolerate? So, and then we have another category. If the column is in a braced frame, or if it's in non-braced frame. Sometimes we call that sway and not sway. So braced means non-sway. Braced frame means non-sway frame. Or sway means just, excuse me, I have to admit 2 more students. Okay, and in order to check if the frame is braced or non-braced, as you might remember from last week, doesn't matter if the frame has bracing or shear wall or not. If it's just frame with nothing, look at this, we call this as a frame, yeah, just moment frame or rigid frame, so it can tolerate the lateral force. If you add bracing like X bracing for steel, actually a structure, or if you fill part of this or whole span with concrete, so you will create a shear wall, so you have frame with shear wall. Then in both cases, we should check to see if the whole system will act like a brace frame or a non-braced frame. As I mentioned last week, having shear wall or bracing inside the frame doesn't mean that at each story that frame must be considered as braced frame. No, we have to check it based on this stability index. Yeah. So how we can calculate this? Just go for the whole story. If it's a 3D frame, you should add all the loads on that story. So for each story, we have to check this Q, not for the whole frame. So for the second floor, then first floor, if it has more stories, one by one. And each case, you should check if the column, if that story is braced or non-braced. Doesn't matter if you have shear wall or bracing or if you don't. Okay, find the sigma PU, find the total shear, yeah, deflection and shear, and LC, yeah, LC from center to center, as I wrote here. And if this one is less than or equal to 0.5, you can consider that as a braced frame, even if there is no shear wall or bracing on that frame, on that story. If it's greater than that, so you should consider that non-braced frame. And even if we have a bracing or shear wall in that story. So that's very important. And I like to see my undergrad students have this knowledge to some, if you start talking to somebody in the field or in an office that you're designing some structures, if you have this knowledge and you can talk about this, it's very good. And as you can see, it's not that hard to find that. Yeah, so it's very easy. So another thing that I mentioned last week, and I'm going to use that this week, is for moment of inertia that we are going to use the K factor for the columns. If you have passed a steel column, you should know this. If you are going to pass this in the next semester, so you need that. So if you learn this year, it can help you on the other class. So for steel columns, steel structure, columns and beams, they cannot get any crack. So moment of inertia is the moment of inertia of column or the beams. That's it. But for reinforced concrete, no. We should know that the beam and column will crack. So we have to go after moment of inertia for the crack section. Can we do we need to go after all those calculations that we did for finding the I effective? No, there is no need for that. So there is a simplified actually solution for that, that we can go based on the code with these numbers. For the column, calculate IG for the column around the bending moment. So that's very important. So for example, if you are talking about this column, and imagine this column is like this. Look at this. I will try to show this like rectangular. And the other column, because of some details that the architect asked us, we had to go with this case. Yeah. So like this. Okay. So IG for this column means that, look at it, bending is around this axis. This is the plan view of the cross section of the column. That's the plan view. That's the cross section. For example, 30 by 20. So IG means moment of inertia around the bending axis. As you can see, this column will bend this direction. So like this around. So this is your axis. That's very important to know what axis you should consider. Sorry about that. Let me add one more student. Yeah, so that's very important to know about the access, and based on that, you can actually you can calculate IG, means this part should be your B, H3 divided by 12. Just the side of the column perpendicular to the axis, you should call that H. Forget about that moment for eccentricity. Just if you go with I is equal, as you might remember from strength of material, BH3 in the divided by 12. Yeah, that's the moment of inertia of rectangular section around the center line. So in this case, your B should be this one. Your H perpendicular to the axis. That's for this equation for IG. Yeah, so this is your H, that's your B. Go to this equation and find IG. Then 70% of that for the columns. So what about this one? This column still, because the column will bend around this axis, your axis for bending axis for this column is like this as well. So in this case, this one is B, always B parallel to axis, B parallel to axis, H perpendicular to axis for bending. So use BH3 divided by 12 for this, but as you can see here, H is longer than the other side. So remember, BH3 for the moment of inertia, gross moment of inertia, gross section, it should be B parallel to axis bending moment axis, and H perpendicular to that center line. For that column, the same. Just this is very important. Otherwise, you will consider IG wrong. Yeah. So what about beam? For the beam, if you are working at this beam, so cross section of this beam, imagine if this is rectangular, yeah, cross section. Bending for this is this one. So how can I call this? Again, be parallel to bending moment axis or center line, H perpendicular. Use the same equation, BH3 divided by 12. Yeah, B, H3, this is H. Yeah, this is H. Okay, BH3 divided by 12, and then 35% of that for this case. But if you have a slab and rectangular beam that they pour together and there are rebar involved between these two, yeah. So in this case, you can consider 75% IG for this beam. Again, rectangular section. Don't go after T section. No, just again, consider that as rectangular, but two double of that as your I crack. So calculate IG for the beam for T shape, then 35% of that times 2. So for this one, 2 times 0.35 means zero point 0.7. Yeah, zero point 0.7 times IG for this beam. But if it was rectangular only, just 0.35 IG. So IG will stay the same. That's important for rectangular. Yeah, 35% of IG. IG is rectangular shape for both of them. This one, 70%, double of that, because the T, the flange will be add to the moment of inertia for that case. So in this case, just rectangular and rectangular, but this is zero point 0.7, that one 0.35. So where are we going to use this? Today, you can see for finding the K factor for the columns, we need to use the moment of cracked moment of inertia for the beam and columns. Okay, so that's a quick review from last week. Is there any question on this one?
Professor, can you repeat the T section and the T section beam?
For the T section, consider this as a rectangular like this one. Forget about the flange. Yeah, calculate the IG, but at the end, instead of going with 35% of G for the beam, consider double of that 0.7 IG. So you have T section, but calculate the rectangular beam, find IG for rectangular, then zero point 0.7 IG should be considered as I crack for this T section. Is that clear?
Yes.
Perfect. Okay. So like always, if you have question, please raise your hand or just talk, and then I will stop and I will go after your question to answer your question. Even if we pass that slide, don't worry. I will back to that slide that you had question. Okay. So let's go after today. Okay. Today we are going to learn about brace frame, slender columns and brace frame. For other case that is non-brace frame, it's a little harder. I will consider that for graduate studies. It's very similar. If you learn this, you can learn that even by yourself. Yeah. But if you learn this, I like to learn one of these completely, the other one should be easy for you. So remember, for braced frame, what does it mean? It must have just shear wall only or bracing. No, we don't know. We check the Q, and Q was less than or equal 0.05, then we consider that story as a brace frame. So here, I'm not going to ask you to check the Q. I'm not. Just I gave you that knowledge because I like you to have more knowledge. Someday, who knows, you can use it. Yeah, even if you don't need that right now, doesn't mean that you're not going to need that in future. Who knows? So it's better to have that. In this class, I will consider all the actually frames as a brace frame. and then check for slender columns for that frame. Okay, so we are going to find the actually K factor for the effective length of the column. That's very actually the same as the one that we started from strength of material for bending when you have actually that uh, slender columns and it has buckling. So we should find the K factor to see what is the length of the column must be considered for that design. So if it's fixed, if it has brace, or if it's hinge and fixed, hinge, so different cases. Okay, let's start. I will start with a real actually problem. So based on that, you can learn how to use it. Consider that we have a frame. Yeah, that's a 3 stories frame. And this one is rigid frame. It might have bracing system in 3D. Yeah, it doesn't matter if it doesn't show anything here, because if you consider three-dimensional frames, means a space frame for the structure, then the whole system, if it's braced, so you can consider that as braced, or the size of the columns, and you check the Q and it's less than or equal 0.5, so it's braced. So we consider this as a braced frame. And we want to find the K factor for this column AB. You can go with this column, with that. All the columns must be designed. Yeah. So I will go with this. I want to calculate the K factor for AB column in this frame. So it means that I know the size of the column, I know the size of the beams, I have all these stuff. And I know if we have a T section or not, if because I am or you are as a designer, you know if what size of the beam or a slab is poured to the column, you are designing that. Yeah. So we know all this stuff. How can I find that K factor? First of all, go and find the CA. Yeah. So that's the name of this. Yeah, because in all the books they are using this actually Greek alphabet. So the pronunciation for us maybe is not exactly correct because we can't pronounce the same as those guys. But we call this C. CA means at point A and CB. So we have to calculate these two at A, top of the column, bottom of the column. Doesn't matter if you call that BA, doesn't matter. Just top of the column, bottom of the column. That's it. What's the equation? Sigma EI over L for the all the columns that coming to A. Look at it, this is for A. How many columns are coming to A? As you can see, column 1 above A, column B below A. So we have 2 columns are coming to A. So we know moment of inertia. Moment of inertia around what? Around the bending axis. So axis means, so in this, please pay attention again to this. This is very important. In this case, your column is like this or whatever. If your column cross section is like that, doesn't matter. Look at this. This line is your bending axis. That's it. That's that easy. So B parallel to bending axis, H perpendicular to the bending axis. So B H3 divided by 12. If you have a column like this, so again, B is here parallel to bending axis, H perpendicular, the same. Just try to find the correct name, BH, then the same equation, BH3 divided by 12. Bending axis, don't forget. This is very important. Okay, so we calculated moment of inertia for the column I. So we call that I1, yeah. Then calculated for this column, we call this I2, yeah. So I1C for column, I2C for the column. So we have 2 columns here, 1 and 2. Okay. Two, and each one times modulus of elasticity. So E times I1 divided by L1 means length of this column. Yeah, length of this column. What's that length? LC. Yeah, LC means center to center. Look at this. I put that here to just refresh our memory. For this equation, use LC, center to center of the beams for the column. That's the length of the column. Okay, center to center of the beams. So E I1C divided by this length plus E I2C divided by L for this column. Yeah, so I find this one, sigma EI over L for the columns, divided by sigma EI over L for the beams. You can see beam 1 will come to A, beam 2 will come to A. Okay, if I call this I1B for the beam, moment of inertia for this one, and then I2 beam. So should I consider IG only? No, I crack. So for the column 0.70, I calculate BH over 3 divided by 12 times 0.7 for this one. BH over 3 divided by 12, because this column should be 20 by 30. This column should be 20 by 35, or whatever it is. If they are the same size, I1C is equal to I2C. So calculate the IG times 0.7, go times E divided by this LC for this column. Then I2C times 0.7 times E divided by LC for this column. So we calculated this. Add them together, that's for the column. Do the same for the beams. I1B then times E. I1B is IG times 0.35. It's a rectangular section times 0.7 if it's a T section. So you should know, if I give you T section, 0.7 of this times E divided by center to center of the columns for the length of the beam, plus I2 beam times 0.7 if it's a T section, times 0.7 times E divided by this length of the beam. Each beam I1B times E divided by L1, I2B times E divided by L2, like the columns, each one separately. Then add the beams together as well. So all the total of the columns divided by all the total of the beams. That's it. Yeah. So you can calculate CA. Do the same for this one. Do the same. You have one column, two column at point B, find the sigma based on the crack section. Then beam 1 at B, beam 2 at B, find those two, EI over L based on the I crack, add them together. Then for the columns, total column divided by total beams, you can calculate CB. So we find CA and CB. Perfect. Then go to one of these two actually charts. One of them is non-sway frames. It means this non-sway means braced frame. In this class, we are covering this non-sway or braced frame. The other one, sway frames or non-braced frames. Yeah. So we are not covering this one. This case is easy, even if there is no title. Imagine you have this, but there is no title between those two. How can we find which one is for one? Whenever this is your K factor, K is between 0 and 1. Over here is 0.5. Between 0 and 1, that's for non-sway or braced frame. Always, always remember, if there is no title, the K, when K is less than 1, that's for non-sway or braced frame. When K is more than 1, all to the infinite, so it's for sway frame or non-braced frame. Yeah, so we will cover this one. Okay, what should we do? But they are, how to use them? They are similar, exactly the same. But this one will give us K greater than 1 This one will give us k less than 1. That's it. For for actually braced frame, k must be less than or equal 1. That's it. Okay. How can we calculate this? We find PCA and PCB. Okay, go. And PCA, for example, we got 3, for example. PCB, we got 1, for example. Just connect them together and read this number. That's your K factor. Yeah. If I, by mistake, use 1 over here and 3 there, you will get the same answer. Don't worry. So A and B just doesn't matter which one is A, which one is B, but do them correctly. So columns to this point divided by beams to this point, not column to that point divided by beams to this point. So it's wrong. So do it for A and B. So doesn't matter you consider 3 here, 1 here, or 3 here, 1 other side, you will get the same answer. Yeah, but it's better to always follow the instruction so you will not miss anything. But if you don't know, you mix this stuff, it's hard to remember what you did, and it's easy to forget something and make mistake. Okay, so always follow this instruction. That's it. So if you learn this, you are good for a steel structure, for you are good for concrete, for you are good for wood structure, masonry, for everything. That's the same method. But some of them, they don't have crack section. So you don't need to find 0.7, 0.35. No, for a steel, there is no need for that. But for the reinforced concrete, yes, you have to go after this. Okay. Is that clear for everybody? Or do you have any question on this one before I go to the next one?
Yes, Professor, what is the L for the beams?
For the beam, center to center of the columns, center to the center of the columns. A span of the beam is this one. Good question. Any other question? Okay, so don't forget, whenever you have a question, even if I pass this slide, don't worry, ask me, I will back to this and I will give the information to solve your problem. Okay, so we are good so far. We could calculate the effective length of the column. That's important. You can see where do we need that K factor. Okay, let's go to the next slide. Next slide, actually, we will go after other step-by-step solution for slender columns. How to calculate slender columns in braced frames. Just remember, slender columns in braced frame. I put this here in yellow. That just don't forget. It's not for non-braced frame, for braced frame. Okay. So first of all, we have to find the magnifier actually coefficient to magnify the moment. Whenever we have slender columns, we have to find this magnifier coefficient delta to increase the moment. That's it. The only thing that we have to do. Then go and do it like short columns. The rest should be like short columns. Just a slender column, we have to find this delta. That's it. Yeah, we have to find this. Okay. And we have one moment on top, one moment at the bottom of each column. Which one should we consider? Consider the maximum as your M, and we call that M2. You have M1 and M2. Just M2, it means that the maximum between those two. You have 100 and 101. M2 is 101. M1 is 100. That's easy. M1 is smaller. M2, negative and positive, doesn't matter. Go with the absolute value. See which one is greater. Go that one. That's your M2 with no sign here. Yeah, no sign. Okay. That's easy so far. Then we have to find this magnifier factor. multiplied to that one, that's your moment that you should consider for your design. If we calculate this like a short column, we had moment and we had PN, yeah, we had MN and PN, or PU and MU. Then we could calculate, we could design the column. So right now, if we find this, that's your moment, and you know the axial load on the column. So you have PU and MU. We can design that like a short column. So, okay, how to find this magnifier actually coefficient? That's the method. First of all, code asks us sometimes in some frames, the moment on the column is very small. And because of that, code will ask us to calculate the minimum required moment for that column. How? PU for that column, because we are going to design this column. We know the PU on this one. Okay, PU times zero point 0.6 inches. Everything here is inch, plus zero point 0.3 times H. What's the H? This H is the same as before. That H is parallel to E. Yeah, parallel to E. Perfect. So this H, we know this. Zero point 0.3 times H per inch plus zero point 0.6 times PU, we can calculate that's the minimum moment required, kips inch or pound inch, because this is inch. If PU is inch, inch pound, or kips, inch kips. Then compare that with the maximum moment between the top and bottom. So M2. If M2 is greater than that, that's M2. It's a minimum greater than your M2. Call this one M2. That's it. This one, you call that M2, and forget about that M2 on your column, because you find the minimum is more than the maximum moment on your column. Then we have to go with this one. Okay. So right now we have this. Then how to calculate this magnifier factor? That's the equation. Cm divided by 1 minus Pu, load on the column, divided by 75% of Pc. What's the Pc? You can remember that from strength of the material. Yeah, Euler actually load on the column that can create buckling. Yeah, critical load. Yeah, Pc. What's that PC? That's the equation. Yeah. So one by one, I will go after this to give you the information. Then you can find delta. First of all, PC. PC, that's the equation. Pi square EI effective divided by KLU. What's the LU? Look at this. If you have beam is not thicker than a slab, so from bottom of the beam to top of the slab, that's your LU. You should consider that LU here. Those are important. EI effective, there are different methods in ACI. One of them is harder and one of them is simplified. So we will go with the simplified. So EI effective is this one. IG, what's IG? IG for the column around the bending axis. Bending axis, I showed you one more time. I'm showing this. Please put note for yourself. Yeah, please write something, because later this stuff, you might not be able to remember this. If your column cross section is like this, the column by itself is your bending axis. That's that easy. Yeah. So IG, consider this B parallel to this one. Yeah. And consider this your H. As you can see, this one is exactly the same as the one that we knew. Why? Because eccentricity for here is like this. That's your eccentricity. Yeah. Your P should be somewhere around here because you have moment at this side. So you have E. So this E parallel to H. Yeah. So as you can see, that's the same as ACI. Yeah. Just remember, B and H, always for IG. Do I need to reduce this here? No, because it's not I crack. It's IG. You shouldn't go with 35%. IG gross. That's it. BH3 divided by 12. That's it. EC for the concrete, modulus of elasticity for concrete. I will give that to you in future. You as a designer, you know based on the code. EC is 57,000 square root of Ephraim C. You can remember that, yeah? So at the first or second class, we went through that EC, how to calculate EC based on the code. Okay, so that's your knowledge. If you can remember, go back to the or go back to the code and you can read that for the material. That's it. Then divided 1 plus beta DNS. So what's that? NS means non-sway, means brace frame. Non-sway means brace frame. Okay. What's the beta D? Make that easy to remember. That's the equation, how to find that. If you go with this, sometimes it's hard. What does it mean? Maximum factored sustained axial load divided by maximum factored axial load associated with the same load combinations. Okay, so if you're checking this column for load case one, because if you have, for example, 5 case load or 3 case load case one, load case two, load case three. So you have to design this column one for load case one from start to the end. Then for load case two, start to the end. Then load case three, start to the end, and see which one needs more bigger size of the column or more rebar. That's your final answer. So it means that for the same load combination, it means that you shouldn't actually just combine these two together. No, go with this load and maximum factored axial load associated with the same load combination. Just here, then here, then here. It means that design the column here, put it away. Design the same column based on this loading. You have different moment, you have different axial load. Design this and put it away. Then for the third load combination, design this. Between those three, pick the maximum size and the rebar that you need. That's it. So your beta DNS should be total dead load for that load case on that column. You know what's the force axial load on this one, and what's the axial dead load plus live load, or just the dead load and live load. Because when you have these two based on the tributary area on the column, you will get that P. So you can go just with the dead load that you started on the floors. This is the floor dead load. This is the live load on the floor, or all those stuff. So dead load or PD, PD, yeah, divided by PD plus PL, dead load divided by dead load plus live load. You can see an example. But right now, just I'm going to give you information. Then when I solve that example, it should be hopefully easier to absorb that. Okay. So we know all this stuff, then find EIO effective based on all this information. Then put that in this equation. K, we calculated K. This is the K factor that we calculated on the last slide. Yeah, effective length, column length factor. That's the K. K, LU, we know bottom of the beam to the top of the slam, length of the column. That's it. We calculate PC. So we know PU, we know PC, we have to calculate CM in order to find delta. Okay, what's that CM? CM is moment modification factor. And that's the equation for this. Look at this. CM is 0.6 negative 0.4 M1 over M2 must be greater than or equal 0.4. You must be less than 1.4. So if you calculate CM was actually 0.38, the answer for this, it's not acceptable, must be at least 0.4. If you calculate this and you got 1.42, it's not acceptable. It shouldn't be more than 1.4. consider that 1.4. Okay. Then, as I mentioned, M1 and M2 at first they had no signs, but right now, based on the directions, you have to pick a sign for this, and that's important. Imagine these are M1 and M2 on your column. I don't need to know which one is greater than, doesn't matter, because I'm looking on the curve. In this case, the curve is important. M1 is the smallest one, positive. M2 is the maximum one, positive. Both of them has no sign, but here we are going to consider positive for the total or negative for the total. How? If the moment that you calculated based on the moment analysis, you did that by your hand, or you got that from the moment analysis from one of those softwares. Yeah. At the end, they give you the directions. So those directions are important. We need them. Doesn't matter. Some of those this direction they call that negative. Some of them they call that positive. Doesn't matter positive or negative. Those are not important. That's based on the sign that they assign for that program. Just we need to know the direction. Okay. If you have a column that M1 and M2 will create double curvature, as you can see, look at it. This one will push it in, the top one will push it in other direction. So you will get double curvature on the column. This one, both of them will create single curvature. This one is more critical because it will bend this. Then if you have point load on this load times this distance, that's delta, will give us additional moment, P delta effect. And because of that, we are going to calculate that magnifier factor. We want to magnify the moment because of the P delta effect. If it's just deflect, then the weight that is on top of this column will create moment, that force times this distance, and will be add to the moment. How can we consider that? That's the equation. I hope it's completely clear. If it's not clear, please let me know. Because if you understand the concept, so you can absorb that easier and faster. Okay, so if you have this case, you should consider M1 over M2 negative. Why negative? Because negative times negative should be positive. You will get bigger CM. Bigger CM will give us bigger magnifier factor. It will increase the moment even more. As I mentioned, if you get more deflection, you will get bigger P delta effect moment. So how we can consider that? By this one, consider this negative. This negative will give us bigger CM. Bigger CM will give us bigger delta. It means that magnify even more the existing moment on the column. That's the way. If you have double curvature, as you can see, the deflection should be minimum. So in this case, the P delta effect is not that critical. So we will get that positive. So positive times negative, you will get negative. This one will be reduced from 0.6. So you will get a smaller CM. A smaller CM, a smaller delta, a smaller magnified moment. So it means that it's not that critical P delta effect. Yeah. So those are very important. And please let me know if you have any question or if any part of this is not that clear. Another part that these are the notes I put for you from ACI. Please pay attention to these small notes. Yeah, it can help you a lot whenever you are going to after design of some columns. So it's very good to know this stuff. M1 and M2 are factored moment. So those are MU. Just remember, those are factored moment, MU, like PU. We call that M1, M2, but that's MU1, MU2. But because on the code, they show that with 1 and 2, with no U, so we are using the same. But those are factored moment. Another one, Cm is equal 1 for the columns with transverse load applied between the support. What does it mean? If this column is at the front face of the structure, and because of the front face of the structure, you have wall connected to the column, and you will get load, lateral load caused by uh, or earthquake to the wall, and the wall will be transferred that to the column. So in this case, you will get transverse load between the supports. Look at this. Over here, we had nothing. We had the moment on top based on the earthquake or wind. But if you have lateral load plus those moments, in that case, you should consider CM equal 1. There is no need to calculate CM if you are in this case. Please pay attention. If in exam, if in your PE exam, if somewhere they ask you calculate CM, if this is the equation for CM, M1 is here, M2 is here, and then they show the lateral load on the columns, and they ask you based on the moments, and they showed everything. Calculate CM. CM is equal 1. You don't need to calculate that. Pay attention. These are important. If CM is equal 1, if minimum M, if you calculate this one, and this moment is greater than M2, in this case, CM is equal 1 again. Just remember. So if you calculate M minimum was greater than M2, you don't need to calculate CM. Consider CM is equal 1. Okay, let me answer one of the chat. I know he asked question a long time ago, but I didn't want to stop at that time. Okay, to determine that's a question, the sign of the moment, we have to draw the moment diagram. Not the moment diagram, just show the moments. Yeah, based on the program, based on hand, actually moment distribution for your column, whatever you did, just based on the loading that you have, you know that the moment based on the slope deflection, hopefully you can remember that it has direction. So at the end, you know what is the moment direction on your beam or your column. Those are the moment. This is not the moment diagram. This is not moment diagram on your column. No, that's the deformation caused by the moment. That was good question. This is not moment diagram. No, this is the deformation caused if you have a moment pushing this in, another end pushing this, the column will be deflected like this. This is the deflection. Yeah, this one, the column on top will go this way, at the bottom opposite direction. So your column will deflect like this one. So these are not bending moment diagram. These are deflection of the column under the top and bottom column moments.
So
That was good question. Yes.
those directions we just assume and then stick with them.
No, you shouldn't assume. You have to obtain them from your moment analysis for the design. When you analyze the frame, you have all those knowledge, the direction of the those moments based on different load case. Maybe at the bend load case 1, you have this kind of moments. Then you have to calculate and your column. The load case number 2, you have to start all over again with PU and MU. And for that load case, you might have this kind of moment. So it will differ from the different load cases. Yeah. And you have to design your columns for all your load cases separately. Do not combine the load cases. Load case 1, complete design. Load case 2, complete design. And for each one, you might get different moment direction based on the moment analysis for that frame. Did I give you the answer?
Yeah, it makes sense. Thank you.
You shouldn't assume anything. No assumptions. You have to obtain those from moment analysis, from software. Do that by your hand. Go with slope deflection method, whatever you know. Find those and see the direction and show the direction to then make decision if you have to go with positive or negative based on the direction that you got. Okay. If you have question, please just let me know. I will go after the answer for that one. Another thing that is important, always do we need to consider slender columns? There are some codes that sometimes there is no need for that. What's that? Calculate for braced columns, yeah, braced frame, non-sway structure. This is the one that we are going to learn in this class, yeah, braced again sideway or non-sway structure. When you are in this category, calculate KLU, means bottom of the beam to top of the slab, over R. What's the R? I wrote that here. Look at this. You don't need to do anything. As you can see, H is parallel to E, like ACI, and B, the same as BH over 3 divided by 12. Exactly the same. So calculate radius of gyration. That's a real equation, but simplified is 0.3 times H. That's it. So if this is your H or this is your H, depends on if the eccentricity as this one is your H. So 0.3 times H, or for this case, 0.3 times that H. Remember, don't forget to pick the right H. H is not the bigger size, is not the small size. No, H is parallel to eccentricity. That's it. Okay. And in the frame, if you have the frame, if you don't know where is the eccentricity, just the column, consider that as your center line of your column. Yeah. So if this is the column in this frame, so in this case, your column should be like this. This is your center line. This one is your eccentricity is this one. This is your center line perpendicular to your edge. Always put a note for yourself. This one is exactly the same as this one. Just remember. But eccentricity here you can't see in the frame. Eccentricity, because you have moment at this direction, eccentricity should be somewhere around here. That's your E. Look at this. Exactly the same as this one. Parallel to E is your H. Parallel to E is your H. The same. But in frame, if it's hard for you to remember, how can I find the eccentricity to see which one is parallel? The line of the column is your bending axis. That's it. And this is your H. When this is your H, that's your E. That's it. Yeah, just please put a note not to make a mistake during the test later or during the exam in this class. Okay, you can calculate R easily based on H equal per inch. Yeah, then what's the calculate this one, K LU over R. So LU per inch, R per inch, K factor we calculated from that chart. Yeah, so we have a number for this, for example, 24.8. Then go and calculate minimum of these two, 34 plus 12 M1 over M2. So M1 over M2 is positive or negative. How? We learned that on the last one. Yeah, we learned how to consider negative. If your moment M1 and M2 create single curvature, negative. Double curvature, positive. So with the same positive or negative come to here. If it's single curvature, consider negative. Double curvature, consider positive. Yeah. So you can calculate a number here. Compare that with 40. Between these two, pick the minimum. Okay, between these two, minimum. So for example, you got 32 here, total of this 32, between 40 and 32, 32. You got 28.4. So your 28.4 is less than minimum of these two. I consider 32. Yeah, 28.4 is less than that. So in this case, slenderness is not important. Consider that as a short column. That's it. So what should I do? Should I go and calculate all those CM and delta and then come to here? No, start from here. Yeah, calculate KLU over R, compare that with minimum of these two, If it's less than minimum, so your column is not a slender. Go and design based on the last week. That was easy. But if it's a slender, it means that your number is greater than this, then you should consider that a slender and do the same as what we did for CM, PC, and find delta, and then M2 times delta is your MC. Yeah, whatever we learn, that's a slender column. Follow that one. If your K, LU over R was greater than minimum of these two. If you have non-braced against sideways, that's not our class for this. It should be for grad studies, but exactly the same is not that hard. In this case, the equation is just if KLU over R is less than 20, consider that as not non-slender column, is just a short column. But if your KLU over R was greater than 22, you should consider that a slender column. So in this class, we should check this one. Easy? Any question? Or hard? Any cases, I'm ready for all the answers. If it's hard, let me know. If it's easy, let me know. If it's good or you have any question, just let me know. Okay. Hopefully, I think you are following me. When you are not asking question, it means that so far you have no problem, or you are waiting for the example. Maybe you have some questions, but you see, okay, let me go through the example. Maybe in the example I can get all the answers. Okay, that's example. First of all, I know that your K should be less than equal 1. Why? Because we are working on non-sway frame, and we should go after the chart that K is less than or equal 1. Perfect. So we know that. Imagine we are going to design a column, this column, and we use different loadings. Yeah, we have different loadings. It's not just one, no, different load cases. But the results will come for just one at a time. So for one load case, these are the results. Yeah, and this column. Okay. Columns are 18 by 18. So that's easy. As you can see, we consider this is your E. So this is your H. Yeah, eccentricity parallel to this one. So column 18 by 18. So H and B, they are similar here. It's not that hard. But try to go with the code and find which one is H, which one is B. Just practice this. Okay. And we have a slab, and the beams are 12 inches by 48. Yeah, look at this. That's very thick web, short actually depth. That's a special beams that the architect just asked them, I don't want any beam thicker than 12 inches. That's very hard to design. Very hard, because especially if you have big spans, each span is 24. Look at this, 5 bays at 4 feet means 24, 24, 24. We have the length of the beams, 6 stories at 14. So 14, 14, 14, each one is 14. Okay, so, and the loadings are PU. They gave us this load as after analysis of the frame. These are the loading that we got for load case number 1 or whatever for this column. Yeah, column C3. Okay, we have to design all the columns. This is just one of them for load case 1, for example. Dead load 230, live load 173, M top 2 kips, and these are the directions that we got from the analysis by hand or a machine, doesn't matter. These are the directions. They gave us positive, but these are this direction. Then this side, again, we got positive, but doesn't matter. Look at it, the code, the machine, the program that we use, they give us this positive. This direction at the bottom, negative. But that direction, the same direction on top, believe me, A lot of program software, they have different direction based on their own program. We should follow them. If one program is positive, doesn't mean that for the other one is positive. Maybe the same direction, they show that with negative, but same direction. So we will show that with negative and positive based on the direction that we got from the program. Okay, so M top, M top, M bottom, M bottom. Yeah. So these are the curvature. Look at this. If I go with this, just I show that to you to just understand this better. Just practice. We have these two moments, you will get double curvature. These two moments, you will get a single curvature. Yeah. So that's easy. How can I find? These are not actually factored load. It's not PU, MU. No, those are unfactored. So what's the PU? 1.2 dead load, 1.6 live load, 1.2, 1.6. That's PU. MU 1.2 times, for example, I will go with the top one, 1.2 times 2 plus 1.6 times 108. You will get 175. What about the bottom one? 1.2 times negative 2. Look at it. Those are opposite direction. Opposite direction. So I will go 1.2 times negative 2 plus 1.6 times 100. You will get positive. And the positive means this direction because they showed positive this direction, negative other direction. So if the answer for MU after I factor those, I got negative, I should follow this one. If I get positive, it means I should go this direction. So for M1, you will get positive. For M2, you will get positive. So positive for M top, positive for M bottom. So we know the direction of the moments and we know the amount. So what's the MU? Because that one, 2 times 1.2 plus 1.6 times this, 2 times negative 2 times 1.2 plus 100 times 1.6. For sure, this one is a smaller. So the factored moment for this one should be M1. That one should be M2 because maximum, minimum, forget about the signs, just absolute value. Still, that is maximum. The other one should be minimum. Yeah. So these are the information based on the stuff that we know. F prime C, E, C, F, Y, we have all these stuff. Yeah. And the columns are 12 by 48, but T-shaped beams. This 48 is not the flange. No, it's the web. I wrote that here. But we should consider it as a T section. So it means that 2 times 0.35 times the moment of inertia IG. Yeah, that's because of that. We need to know if it's a T section or a rectangular. Okay. Then I wanna go and find a K factor. How can I find that? For the columns, find IG, BH3. H should be parallel to E or perpendicular to bending axis. Both of them are the same. Here is not important. But for crack section for the column, 0.7. So I over LC, okay, we had LC, LC to center 14 feet, from bottom of the beam to top 13 feet. Those are important. So for this actually K factor, you should go with LC. Yeah. So 14 feet times 12 convert to inches. So I over C, because I is this one, inch, and then H, LC should be inch as well. Okay, we calculate this. For the beams, it should be T section. And for rectangular 48-inch BW, H was 12. So 12 in the power 3, because H times B divided by 12, because it's T section times 2 times 0.35. You can remember why 2 because of the T. So this is a crack section. I over L. How can I calculate L for the beam? As I mentioned, column to column distances 24 feet. Yeah. Each way 24 means column to column center line is 24 feet. Okay. So we have divided by 24 times 12, convert to inch. So we calculated I over E. So do I need to use E? Look at this, because I have EI over L for column divided by EI over L for the beams. Because I have E on top and bottom, so I don't need to use that E, because EC is constant for the column and beam. If you have EC for the beam different than EC for the columns, then yes, you E for the columns and E for the beams, because they are not the same. But in this case, you can cross them out. Yeah. So in that case, you don't need to do that. As you can see, you have two columns, and they made that simple. All the columns are 18 by 18. All the beams are 12 by 48. Okay, so at A, I have two columns, EI over H or L for this, two of those divided by 2 EI over L for the beams. And because E is not that important, because we can cross them out, so I can write 2I over L for the columns plus 2I over L for the beams, because the height of the columns similar, size of the columns similar, height, length of the beams similar, length of the size of the beams similar. So just this problem is very easy, yeah, because everything is equal. So top column at A, top column at A, bottom column at A, two columns, they are the same, 36.5, add them together with no E, because we have E parentheses, both of them, and E parentheses for the beam, you can cross them out. And then for the beams, 16.8 EI over L or I over L for one beam. The other beam is exactly the same. Then find phi A and phi B, they are similar. Yeah, in this case, they are equal. Then what can I do? Go to that chart. Yeah, look at this. Go after this one, non-sway, 2.4, for example, and 2.4. Connect them together and read this number. That's your K factor. That's it. I hope you got this. Now we are here. Let me ask you one question and give me the answer. If I ask you in an exam to design this column, so A, B. At A, how many columns do you have for this CA, sigma EI over for the columns? How many columns should I consider at point A?
One.
One. How many beams at A?
One.
Perfect. How many columns at B?
0.
Two.
Two. One on top, one at bottom. Yeah. Two columns. How many columns at B for this column?
Two.
How many beams at this B?
One.
One. Look at this. You have one. Over here, you have one at the left, one at the right. One on top, one at the bottom. Over here. No, nothing from top, just one at the bottom, one column. One at the right side, that's it. At the bottom, one top, one bottom, one right, that's it. So do the same, but you don't have two columns, you have one column, one beam. Over here, two columns, one beam. That's it. Just the same equation, just see how many columns, how many beams do you need to consider for A and B. If I ask you to go and design this column, so over here, there is no beam. So what should I do? Here, you don't, I call that A and B. And because of that, I wrote that phi B, yeah, or PCB, yeah. That's at like this one, AB, I call that A, B. If you have fixed connection, there is no need to calculate this. Just consider CB equal 1. Then for A, what should I do? You have two columns, two beam. Follow this instruction. Calculate PCA. For PCB, just because it's fixed connection, PCB equal 1. Always. Still a structure, always. Any kind of a structure, that's the equation. Then, if you have just not rigid or fixed connection, you have a pin connection. In this case, the CB is equal 10. These two always are constant numbers. But for the top, you have two columns for the A, one column, one beam at the, you can calculate PCA, and for PC, just 10. Is that completely clear? Okay, like always, if you let me read one chat. So do you use 10 for pin? Yes. For pin connection, just you should consider PC. B is equal 10. Calculate PCA, and with PCA equal whatever it is, and PC 10, go to that chart and read K. If you are in this case, calculate CA, and with CB equal 1, go to the chart and read K. That's it. Is that clear? Answer to this one? Yes. Okay. Thank you. Let's go after our actually example. Okay. Based on CA and CB, for this case, we went to that chart and we read K equal 0.87. This is correct. Why? Because it's less than 1. If it's more than 1, was wrong. It means that we used the wrong chart. Okay. Then calculate KLU over R. What is the R? 0.3 times H. H parallel to E or perpendicular to bending axis. Okay. Calculate this one. What's the LU? From bottom of the beam to top of the slab. Look at this. We use LC already, and right now LU. Okay. Based on this one, is times 12 convert to inches, or 0.3 times 18 inches, we will find 25.1. At first, we have to check if we should consider this as a slender column or not before we go and calculate delta and all those stuff. So we started with this. Then we have to convert that with the maximum of those two numbers. Can you remember? 20, we should go with 34 plus 12 M1 over M2 and compare that with 40. So M1 over M2, what's the M1? 1.1 times negative 2 plus 1.3 times 100. This is M1 because it's less. 1.2 times 2 plus 1.6, that's the maximum M2. So M1 over M2 and negative. Why? Because both of them we will get positive and positive based on the information this gave us. When you get positive and positive, otherwise they show that negative and the other direction. We got that positive and positive. It means that we have single curvature. So it means that we should consider that negative. Okay, and because of that, we put one negative here. Please pay attention to this. This is very important. Otherwise, you will make wrong decision and it's completely wrong direction. So we will get 23.2. That's the answer. Between 23.2 and 40, pick the minimum of these two. Minimum 23.30 and 40 is 23.3. As you can see, KLU over R is greater than minimum of these two. It means that column must be considered slender because it's more than the minimum of these two. If it was less, you should go after short column. So it's slender column. We should go with the slender. So we have to follow the instruction. First of all, we have to find the minimum M to compare with our M2. And what was that? PU times 0.6 plus 0.03 times H. H exactly the same as before, parallel to E, perpendicular to bending axis. Okay, inches, 0.6 inches, 553. Where is PU? PU we calculated here. Look at this, 1.2 PD, 1.6 PL, live load PL. 1.2 dead load. Yeah, I'm repeating this stuff to make sure that you got them correct. Okay, so if you calculate that, you will get PU times that 53 feet cubes, and it's less than the M2 that we calculated 175 foot cubes. Yeah, this is foot inch, kip inch divided by 12 converted to foot kips. And this 12 is just for converting to foot kip. If you compare these two stuff, you can see M2 that we had is bigger than this minimum. So we will go with ours. But if, for example, we got 190, we had 175, we should go with 190 here and consider M1 whatever it is. Always M2 is on top? No. M2 might be at the bottom or might be top. Doesn't matter. But that number, if was greater, it should go here for M2 because this is M1. We compare with the M2. But here M2 was greater than that one. We are not changing anything. And we know that we are getting a single curvature, means negative. Okay. Those are still those negative M1 and M2, and then find CM. How can I find CM? Go to this equation. M1 over M2 must be negative if you have single curvature. Yes, we have single curvature, so negative. What's the M1? That M1 that we calculated from the start. M2, and it's 0.94. Greater than that, less than, so we are good. What's the beta DNS? 1.2 times dead load. What's that dead load? PD. Yeah, PD 1.2, 1.2 PD plus 1.6 PL. That's it. Yes, what's the question, George?
Why was the M1 over M2 negative again?
Look at this. M1 and M2, as you can see, both of them are pushing this at the one direction. So you will get single curvature. And for single curvature, as you might remember on this slide, we call that whenever you get single curvature, consider M1 over M2 negative. If M1 and M2 create double curvature, consider M1 over M2 positive. Yeah, that's based on the code. These signs are based on this. If you change it, then you have to change this one as well. Because of that, follow the instruction. That's exactly per code. You will not make mistake. So M1, M2 create single curvature. And because of that, is more critical. We consider that negative to give us bigger CM. Negative times negative, positive, positive plus something, it's bigger than if you go with a positive. Yeah, if you go positive, you get negative minus something. The other one, negative times negative, positive, positive plus 0.6. So you will get bigger CM. So whenever you have single curvature, you should consider M1 over M2 negative. Did I give you the answer?
Yeah, then what would the M's have to be to get that positive one? Because I was thinking these ones were going to create the positive one.
Yeah, sometimes in different load cases. As I mentioned, you have to design this column for different load cases. Different load case means when you have just dead load plus live load. When you have dead load plus live load plus wind load. Dead load plus live load wind other direction. Dead load plus live load earthquake this direction. Dead load plus live load earthquake other direction. You have 5 or 6 different load cases. In any load cases, different load cases, you might get this curvature or that curvature. Do you know what I mean? So that's important to see. You are working at one at a time load combinations, one at a time. And for each case, you have to figure it out if you will get single curvature or double curvature for each one separately. And do your design all the way to the end. Then back and start for the other load combination. And other one, you might get, again, double curvature or single curvature based on the analysis that you did and the loading that you had on the frame and the answer that you did by hand or with the software. You have to read those and show them on your column to see which case you should consider negative or positive. Is that clear?
Yeah.
Okay. I'm sure it's not 100% because you have to work with this. You don't know, maybe you can't remember right now. I'm talking about everybody. You can't remember the analysis for the frame, how you can use, how to use the slope deflection. For sure, those are something that you have to remember, but not right now. In this class, I'm information like this, and just you have to make decision: single curvature or double curvature. And I gave you the other slide. When go with the single with negative, when you go with the positive. Okay, so because we have single curvature, negative, so we use negative. That's our CM. And beta D, we calculated that dead load divided by total load. That's it. And then go after EI effective. That's the equation. What's the IG for the column? BH3 divided by 12. That's it. Times EC, we know EC. All of them the same, actually the same units: pound, inches, inch in the power 4, everything the same unit. Yeah. In this case, we used a pound and inch. So these are the numbers that you can see. We plug in all those beta and the IG and EC inside this equation. And at the end, you can see that's the answer, EI effective. Put that in PC. You have to find PC in order to be able to calculate delta. So PC, that's the equation, pi square EI divided by KLU square. LU means from bottom of the beam to the top of the slab, times 12, convert to inches. K, we calculated that before. That's your PC. Okay, so with all this stuff, go to this equation delta, and you, for this delta, you calculated CM before 0.696. PU, that's the load on the column, 553. 0.75 PC that we calculated, 1.15. So your delta must be greater than or equal 1. Delta cannot be less than 1. Must be greater than 1 or equal. So it means that with the same PU, just increase your maximum moment with this delta. Multiply this, and because of that, we call that magnifier factor. So the question, should LU equal 14? LU, let me show that to you one more time. LU is 13. See, LC was 14. Yeah, from center to center was LC, from bottom of the beam to the top of the slab was 13. Yeah, but still, if it's not clear, please let me know. Let me read. Okay, perfect. Good. So right now we calculated that delta means increase your maximum moment 15%. Okay, MC is equal delta M2. That's it. That's we are done. Then go with the chart from ACI, calculate KN, PU over phi, PF from CAG, Rn, MU divided by D, and we want to use 4 sides equal. And what's your gamma? Gamma is 18, as you might see from top. We show that here. We consider 2.5 inch to the center. Yeah, 2.5 inch. So your gamma should be 18 minus 2.5, minus 2.5 divided by 18. That's the equation. Yeah. So go and find gamma is 18 minus 2.2 times 2.5 means 5 inch, divided by 18, 0.72. As you can see, this 0.72, you have to go between 0.70 and 0.80, and then calculate this rho g. So that's part of the last week knowledge. So I didn't repeat that here. You have to find rho g for 0.7, rho g for 0.8, and between those two, interpolate and find rho g for actually 0.72. And you will get 0.026. That's the chart we have to use. F prime C 4, Fy 60, 0.7. In this case, if we go with 0.7, consider 0.72 is 0.7. Yeah, make it simple. So what should I do? Kn, find Kn here, show that here. Rn, show them here. Then a straight line, find the cross section and read this number. It should be two. If it's here, between 2 and 3%. Yeah, as you can see, it's 2.6% means 2.6 divided by 100 means 0.026. This is important. Means 2.6%. 2.6 divided by 100. So AST total should be this R times your cross-sectional area, 18 by 18. That's the total cross-sectional area required rebar. And we will pick number 9, yeah, and number 10 for number 10 plus for number 9. Yeah, in this case, we will get the total of cross-sectional area. I can't see that number, but now I don't have that here, but you can calculate that 1.27 times 4 plus 4 times 1. You will get 8, almost close to 9. Yeah, so it's close to this one. Based on this AST, we picked for number 10 at corners. Always the biggest one will go to the corner for number 10, and the other 4 numbers will go at the between those two. Yeah, so for number, and for the tie bar, because the maximum bar is less than number equal 10 and less, so we will go with number 10, number 3, always. If we had number 11, you should start with number 4. Just remember from the past. So number 3 for up to number 10. After number 10, you should go with number 4. Okay. What's the minimum required spacing for the tie bars? Yeah. The minimum is 16 times of the diameter of the bigger size. Bigger size is 1.27. 16 times of that. Yeah. Means 20.32. That's this one. 48 times of the diameter of the tie bar means 3/8. 18 inches, and minimum the smallest side of the dimension of the column, 18 inches. Between all these three, the smallest is 18 inches. So number 3 at 18 inches. That's it. As you can see, it's not that hard, and that's your homework. And then end of this column. So hopefully we have enough time right now for reviewing any of these slides that you think you have problem. Please let me know. Start your questions.
Can you please review using diagram A6 to find row G? I think you follow like the curvature, but I'm not 100% sure.
Oh, look at this. We calculated Kn and Rn. Look at this. These are our Kn 0.656, Rn 1.159. Yeah, we calculated these two. And based on these two, and what is this mu? This mu is magnified moment. Look at this. This is your MC. It's not M2. As you can see, this is this one. Our maximum moment was 175, but we magnified that because it was a slender column. We magnified that. If it wasn't a slender column, if we calculate KLU over R, it was less than 34 plus 12 times M1 over M2, less than that. So it was just short column. Forget about everything. At the end, you had PU, this one, MU equal 175 without magnifying. And then go through this and find that's a short column. But in this case, just the difference was we had to calculate delta, magnify the moment, the maximum moment. This moment will go to this equation here. That's it. Yeah. So we calculated Kn, Rn with this gamma. We will go, for example, to this chart. So 1.5 something. Yeah. A line here. 6 point or 5.6 something, somewhere around here. So intersection between vertical line and horizontal line will go somewhere around here. Yeah, as you can see, 1%, 2%. We are between 2 and 3. If you measure this, for example, we can reach to 2.6%. Okay, 2.6% is the answer for this problem. Divided by 100, because 2.6% divided by 100 means this, times total cross-sectional area of the column, 18 by 18, means this one. Then we pick for number 10, for number 9. You could go with 8 number 10. It's much bigger than this, but it's way stronger than what you want. So try to be as close as you can. So that's the answer. Did I give you the answer?
Yes, thank you.
Okay. Any other question? Just remember, in exam or any test in future or in real design, if you make wrong calculation and instead of consider that as a slender column, you go with just short column, you made some mistake and the numbers came out with actually not a slender column, then as you can see, instead of considering 2 or 1, you will go with 175. And you will change, you will use less rebar. You must pay attention to all those parts in the code. And those are not hard. Just follow this instruction. And please, like always, solve the example first. Do not jump to the problem. Believe me, I know this is the best way. You think you are losing time. No, you are gaining time. Because when you go after that, whatever you are doing, maybe it's completely wrong. But at the end, you have some answer. You wrote something. You think you did that correct. Please do it first by yourself, not just read. Yeah, do it by yourself. Then you can find if you have any problem or not. Then jump to other one. If you do this stuff step by step, believe me, you can be one of the good engineer in future. Just try to do everything correct from the start. Don't go wrong and then you have to back again and then do something. No, please do it once and correct. How? Review stuff, do the examples first, make sure that you understand this completely, then go after the solution. In future, based on this knowledge and this stuff, then you can solve something that is not in the book. In future, you will be involved with some calculation in some structures that there is no answer in any book. You must create the answer. Yeah, prepare yourself. Prepare yourself. And I'm sure you can. You showed me. In the exam, you showed me most of you guys, you got very good grades. So it means that you can do it if you want. Do it this time. For the third exam, I want you to send me all the homeworks that you did that by yourself. Please do it. Yes, what's the question?
So in this example, we were just verifying the design column can hold the dead load and live load given.
No, we calculated the rebar. There was no rebar. Yeah, based on the size of the columns, we had 18 by 18 based on the architecture, gave us the minimum size. Then we tried to check it. And at the end, this one should be less than 4%. We are good. Yes, it's less. But if you solved and you got 6.8%, so it means that you have to talk to the architect, please, I need bigger size of the column, not 18 by 18, or change your F prime C. Instead of 4, go with 5. Then you need a smaller size of the column. So we designed the rebar. Yeah. So we had the loading. We assume something for the dimension of the columns. Then based on this, we came up with the size of the rebar. Is that clear?
Yeah, it makes sense. And that equation your mouse is on right now, what are those variables that we plug in, the 0.026 times 324?
That's this one. Look at this. That's this one. That's your percentage of the rebar times cross-sectional area of the column. That's AST. Why? Because you might remember that rho percentage of the rebar is equal AST. I will write just AS, hard to write, AS divided by AG. Yeah, I wrote everything. It's not that hard to write that one as well. Okay. So look at this. That's if I call this rho G. Yeah. Percentage of the rebar is equal cross-sectional area of the rebar divided by cross-sectional area of the concrete. Okay. So your AST should be equal rho G times AG. AST is equal rho G times AST. AG. AG, how can I calculate this? AG is 18 by 18. B times H. Yeah. AG is equal B times H. And what is B? What is H? You know that H is parallel to the E or perpendicular to bending axis, and B is other side. Yeah. B times H is your AG times percentage of the rebar will give you total cross-sectional required cross-sectional area of the rebar, 8.42. Then 4 number 10 plus 4 number 9. If you add them together, it's more than 842. So that's good. Did I give you the answer?
Yeah, thank you.
Okay. Any other question? Okay. Looks like there is no question. So actually, today, because tomorrow we have no class. It's a start of a spring break. Am I right? Tomorrow we have no class. Is that correct?
Correct.
Okay. And because of that, I'm not going to have any lab class for this week as well, because next week, then we are short in one. So actually, for the next class that we have, then we have one Tuesday and one Wednesday. Then I can give you, we have one more lab. So just I need one day. So I'm not going to keep you for today because there is no class tomorrow. And I wish you all a very happy Thanksgiving. Enjoy your actually Thanksgiving, and if you have any question, if you are working on these days on this stuff, please just send that to me. Ask your questions. I will check my emails, and I'm not going so my emails, and I will answer for your question. And another things that I'm not sure if I talk to you later or not. If you have not fill out those evaluation forms so far, they ask me to ask my students, please do that. Please do it. It can help me. If I see your inputs, I will read those. Believe me, I like to read those, and I like to use those to make this course even or make this more useful for all the students. So if you, I think I saw one of you guys actually raise your hand. Is there any question? Okay, what's the question?
I was wondering if you can give us a list of all the labs, like the topics that we need to finish.
Actually, I prefer to see you are doing that by yourself, because from the start I ask you, please just keep track of these stuff. Do you know what I mean?
Yeah, definitely. I
I
do
like
have
to
them.
see.
I just want to make sure that I have like each lab with the correct title and with the correct sequence.
Okay, so I will put those together, and I will email to everybody.
Thank you so much.
Okay, I will. I will do that.
Another question I have on the last week's slides. If you can please go to that. It's fall 13.
Let me go to 12 and 13. Okay.
I please, if you can go over how to read the charts and find KN.
Okay, so let me